Complex systems can be hard to manage, and when a system is not well understood, rules for management proliferate. This is because rules are developed to regulate behavior. Behavior refers to how the system behaves and how it reacts to events. Good rules promote desirable behavior. Bad rules promote bad behavior. But bad rules can lead to unexpected, undesirable behavior. Why? Because the system is not well understood. If you don't understand how a system works, you won't design rules that lead to desirable behavior and desirable performance. Once somebody sees that things aren't going so well, they develop new rules to regulate the new behavior. But these new rules won't be so good for the same reason. You don't understand the system. You see the bad behavior, and you develop still more rules and so forth. Whenever you see a complicated system in which there are large numbers of rules, that may be a sign that the system is not well understood, and you have to go back to basics to really understand it. Let's make up a story that gives an example of this. We have a factory. The factory is doing jobs for more than one customer. The management observes that many of the jobs are late, so they need to do something about that. So they come up with a rule. The rule is, do the latest jobs first. Well, this makes sense. That means that jobs won't get to be too late, or at least that's what the common sense says. However, they observe undesirable behavior. More and more jobs seem to be becoming later and later. So this is bad. They need to do something about this. So they come up with another rule. Since there are many different customers, and some customers are more important than others because they have larger orders or other reasons, the new rule is treat the highest priority customers as though their due dates are 2 weeks earlier than they really are. That makes sense. At least the highest priority customers will get the good treatment, and you can make a profit from them. However, what they observe is that the low priority customers find other suppliers, but the factory is still late with the ones that remain. Why? Well, because they don't understand how their system is really working. When a factory makes multiple part types, and those part types differ, they have to change the configuration of machines from being able to process one kind of part to being able to process a different kind of part. Frequently, those setup times are significant. So if those setup times are not considered, then you'll waste a lot of time doing unproductive work, which is changing setups, and therefore you'll waste capacity. Any rules that do not consider setup times in this factory will have to perform poorly. Now, there are two ways of reducing the time that's lost due to setups. One is technological. You can simply change the machines so that the setup times are reduced. Or there's operational solutions, which is to have larger batches so that you have to change setups less often and therefore lose less time for setup change. On top of that, they need a better process for deciding what orders to accept and when to promise delivery of those orders. They also need to understand their factory's capacity. What's the maximum possible production rate that the factory can operate at, and how that production rate is related to the setups. Here are some important definitions. Manufacturing is the transformation of material into something useful and portable. A manufacturing system is a set of machines, transportation elements, computers, storage buffers, people, and other items that are used together for manufacturing. We can call these items resources. Alternative terms are factory or production system or fabrication facility. The last one is particularly used for semiconductor manufacturing. Subsets of manufacturing systems, which are themselves systems, are sometimes called cells or work centers or workstations, and we'll be using all those terms relatively interchangeably. Managing factories has always been challenging, but these days there are more issues that are coming up that make things even harder. For example, there are frequent new product introductions. As a consequence, product lifetimes are very short, and process lifetimes are therefore very short. This leads to frequent building and rebuilding, or at least reconfiguring, factories. There's little time for improving the factory after it's built. It has to be built right. So what do we need in order to do that? We need tools to predict the performance of proposed factory designs. We need tools for optimal factory design. We need tools for optimal real-time management and control of factories. And most importantly, we need manufacturing systems engineering professionals who understand factories as complex systems. Some more definitions. Design quality is the design of products that give customers what they want. Examples are fuel economy in cars, advanced electronics, attractive styling in cell phones. Manufacturing quality is manufacturing products to avoid giving customers what they don't want. Examples of what they don't want are exploding airbags or exploding batteries. This course is about manufacturing, not about product design. Quantity is how much is produced and when it's produced. Quality is about how well it's produced. In this course, we focus mostly on quantity. Much of manufacturing is setting goals and then meeting them. In quality, the goals have to do with tolerances. In quantity, it means delivering a specified amount at a specified time. In general, variability is the enemy of manufacturing. That applies to both quantity and quality. Variability makes it harder to meet goals and requires you to be more conservative about how you set them. There are two basic styles for how factories meet demand. One of them is off the shelf, or make to stock. In that style, items are available when a customer arrives. It's appropriate for large volumes, limited production variety, and cheap raw materials. It's very much like a supermarket. When you need to replenish your home supply of Frosted Flakes, you go to the supermarket and you find the Frosted Flakes on the shelves. If they're not there, you go to a different supermarket to get your Frosted Flakes. With make-to-order, the production is only started after the order arrives. It's appropriate for custom products, products in low volumes, and products that have expensive raw materials. It's very much like buying clothes that have to be tailored. But for both make-to-order and make-to-stock, there are trade-offs in how you manage the factory. For make-to-stock, you'd like to have large finished goods inventories to prevent stockouts. Stockouts occur when a customer shows up and the product he wants is not there. On the other hand, you'd like to have small finished goods inventories to keep the costs low. Inventory is expensive. And we're going to spend a lot of time later talking about the cost of inventories and how to keep them low. Inventory is expensive because of the time difference between when you have to lay out money to buy materials and when later you get reimbursed and more for when the goods are actually sold. In addition, storage space costs money and material handling of storage costs money. There's a potential loss of value due to obsolescence or spoilage while an item is in inventory. And there's also potential loss due to damage or theft or even misplacement. For make-to-order, you'd like to have as much production capacity as possible. That allows you to meet the demand quickly as soon as it arises. You'd like to make early promises and reliable promises for delivery. On the other hand, you'd like to minimize the excess production capacity to keep costs low, because production capacity, which is machines and other capital equipment, costs money. Factory management has to deal with complexity. Complexity occurs when collections of things have properties that are non-obvious functions of the properties of the things that are collected. We'll talk about how things interact in factories later. Non-synchronism, especially random non-synchronism and its consequences. Factories do not run like clockwork. Ideally, as soon as machine 1 finishes an operation on a product, it delivers it right to machine 2 that's able to pick it up and start right away. In reality, that doesn't frequently happen because of lots of variations and lots of complexity in the system.